Okay, so today we are going to go into linear momentum and collisions. So let's go ahead and get started. All right, so first of all, we need to talk about linear momentum. And the official definition is really just the definition of its equation. So it is the product of a system's mass and its velocity. Okay, so you can see it here. In this equation, we have the momentum, which is a lowercase p, and it equals a mass times some velocity. Now you notice that these are bolded, which just tells us that they are vectors. Okay, another way we can do that is, of course, putting a little mark above there. Okay, and just so that we know, or we can remember our SI unit here for linear momentum is going to be kilograms times meters per second, okay, which is really just mass times velocity. Okay, so let's go ahead and look at a couple examples to kind of show you what linear momentum really is. Okay, so here we have a little graphic, okay, and we have three different cars. If you notice, they are all going the same speed, 10 meters per second. Okay, so my velocity is constant here. Okay, excuse me. But if you notice, each of the cars has a different mass. So my first one here, my mass is 5 kilograms. Okay, my second one is 15. And my third one is 35. Okay, so obviously these would be like toy cars. Okay. So if I want to know which one has the most momentum, linear momentum, I will use this equation here to figure that out. Now, some of you can do this in your head really fast and just like, oh, it will blah, blah, blah. But let's go ahead and look at least the two masses here and here to get the two extremes. Okay, so my first momentum here is going to be my mass, which is 5 kilograms, okay, times my velocity, which is 10 meters per second. Okay, so now we can see if we multiply 5 times 10, that's obviously 50. Okay, kilograms, meters per second. Okay, now if we want to look at the second one, or I'm sorry, the third one, this one down here, we have a mass of 35 kilograms and the same speed, 10 meters per second. Okay, so my momentum here is 350 kilograms meters per second. Okay, so as you notice, if we are saying that our velocity is constant, our mass is going to determine which of these three cars has the highest momentum and the lowest momentum. Okay, so this first one is the one with the low momentum, and this one down here with the 35 kilograms is going to be the highest momentum. Okay, so this is just looking at when we vary the mass, what happens to the momentum. Okay, so now let's look at the other case. What if we change the velocity but keep our mass the same? Okay, so here my mass is constant. So my mass is now constant. Okay, but my velocities are varying. Okay, so my velocity for this first one is 0. Okay, velocity for the second one is 10, and for the third one is 20. Okay, so if I go ahead and calculate the momentums here. So for the first one, I have the mass, which is 15 kilograms, okay, times my velocity. And as you notice, this car is not moving. Okay, its velocity is 0. So that means that my momentum here is going to be 0. Okay. If I look at the second one, I have 15 kilograms times my speed, or my velocity. It's going to be 10 meters per second. Okay, so that gives me 150 kilograms meters per second. Okay, now this tells us that as we increase our velocity, okay, our momentum increases as well. Okay, so again, this first one has no momentum. This 15 kilogram car with the 10 meters per second has, you could say, I guess, low momentum and then high momentum. These don't really matter. It's just, I'm trying to give you guys some kind of quantity or qualitative way to look at it, okay, rather than just looking at numbers over and over again, okay? So again, we just want to know or understand the relation of linear momentum to mass and velocity, okay? So let's go ahead and move on now to linear momentum and Newton's second law, okay? And really it just is a different way of calculating force or net force, okay? Relating that to momentum and time. So our net external force here is going to be equal to the change in momentum divided by the time, okay? Now, I wanted to kind of show you guys how this works out. Okay, so we know that our momentum, right, we saw in the last slide that momentum equals m times v, right, or mass times velocity. Okay, now if I want to take the change in momentum, I would need to take the change of mv, okay, and mass does not change, so we could just leave that there, but we will have some change in velocity, okay? So then we want to know, well, how does this relate to this directly? Okay, so let's go back and think of Newton's second law. So Newton's second law, F net, is equal to mass times an acceleration, right? And we defined acceleration as being some change in velocity divided by a change in time, okay? So if I want to plug this back in to my F net here, I can say it's gonna be my mass times my acceleration, which is gonna be, delta V over delta T, okay? And if we want to relate that to our momentum, we see again our change in momentum is the same as mass times our change in velocity. Okay, so we can go ahead and plug that in. So now we have delta P over delta T, or a change in momentum over a change in time equals our net force. Okay? So this is important to understand, okay, this equation here. Now let's go ahead and move on to rearranging that equation that we just discovered. Okay, so again, our equation that we just got is going to be F net equals delta P over delta T, okay? Now, we want to kind of rearrange this because maybe it'll help, or it'll give us another quantity to look at. And so that's what we did here. Okay, so we solved for our change in momentum, And that is going to now equal our F net times our delta T here. Okay. Now, this quantity here that we define is called impulse. Okay. And this impulse is really a change in time. Okay. Or we can also think of it as a force acting over a time. Okay. Which results in a change in velocity for an object. Okay. So this quantity is important for us, okay, to understand, because this is why we need things like airbags. Okay, this is just an example, or some kind of cushioning to kind of take a blow, right? So if we increase the amount of time here, okay, so if we increase T, the force will then need to decrease to keep this in balance. Okay, so let me say that again. So my change in momentum, for that to remain constant, and if I increase the amount of time, okay, my force will need to decrease, okay, again, to keep this balanced. Now, if I do it a different way, if I say I want to increase the force, then my time would need to decrease. Okay, it's the same kind of thing. But the reason that this one matters is because it will allow us to decrease a force. Okay, and that's important because if we, let's say, if we didn't have airbags, okay, this is just an example. If we didn't have airbags in our vehicles, then we would be like hitting the dashboard right away, right? Or the steering wheel, I guess, if you're driving, okay, if you're in a car accident. But if you have some kind of like cushioning here, and then you hit that, and this stuff is, you know, soft, this is increasing the amount of time, okay, to hit this steering wheel or dashboard. Okay, so then it lowers the force. Okay, so this stuff is important. Just want to remind you guys that this stuff does have real world application, and that's why there are people who study physics. Okay.